starting the course. Now we are starting the course. Evet, günaydın. Last week we have been talking about rectifiers, bridge rectifiers, and the waveform, output waveform might be, if you have a resistive load here, you might have output voltage might be something like this. This is so, and also what is important here, since you have input Vs, assume that Vs supply is equal Vm sine omega t. So your average value was calculated, VO average value is calculated, VDC de diyebilirsiniz buna. VO average was calculated. So the half of them is enough. That is pi. That is 2 pi, which means 10 millisecond. This part is 10 millisecond from 1 over pi integral from 0 to pi Vm sine omega t dt. So one value was average value, but that wasn't enough. This is a DC side, output. That one is output. This one is output too. It's a continuous current. If you have an inductance in your network, your current is going to be, most likely it's going to be continuous. So we have also defined for evaluating the DC part, ripple factor. I just review ripple factor, form factor. These two are the main criteria to define the quality of this output. For example, if you have an output like this, if you have an output like that, this is time, this is output, VO, time function. That one is VO time function as well. So if you have an output like this, şimdi göstereceğim. I'm going to show you. Are you happy with this one? Of course we are happy. It's much better. The average value is somewhere there. Average value is somewhere there. So less ripple it has. Okay, so quality of the DC is much better than comparing with this one. Comparing with that one, ripple factor, form factor are important and much better for the second figure here. But these figures have a pure DC and also an AC. So it has AC components in it as well. But also it has RMS value. RMS value means that you are including AC and DC together. So if you look at the equations, then this is a pure DC, and this is also RMS output, RMS current and RMS voltage value. And this is a rectification ratio, DC to that. AC means total output power, actually, but it has also RMS voltage and current product. But if you look at those equations, I have already given those equations to you, but you have to consider now what's going on. That one, for example, the pure AC component is equal RMS square minus DC square. In actual fact, DC square and AC square is equal RMS square. RMS is the total of it. Don't forget. That's important. Form factor, however, represent is more than one, by the way. If it is one, it's nice. It's perfect. But it's more than one. RMS value always higher than DC, pure DC. Pure DC means average value. Ripple factor, however, should be the AC component over DC component. So this also tells you it should be that one. Form factor should be 1. It's always higher than 1, and this should be, should be equal to 0. And the relationship between those, ripple factor is equal form factor square minus 1. There's another definition, you remember that, transfer utilization factor. That is completely different. Than it has a rectifier always has got rectifier has always has got a transformer here. A transformer here, and the rectifier, no matter how many, it's a single phase. So AC, DC. So this one, that one is IS, and the voltage here is VS, supply voltage. VS is Vm sine omega t, sinusoidal. And IS is not sinusoidal, but it's AC. But it's important what I'm saying. I'm going to repeat in Turkish too. Önemli bir şey söylüyorum. Gerilim, voltage is sinusoidal, most likely. Generally, we accept that electric power system is strong and the voltage waveform is not distorted. However, current you draw from your system, that is the load you have. That load might be resistive, might be inductive resistive together, might be resistive and voltage source, R, L, R, or might be resistive, inductive, and voltage source. So these are, it could be one of those simple resistive load, it could be LR type load, it could be battery, for example, RE types of loads, and also could be resistance, inductance, and a voltage source. So these are the load types, and those load types define the current of I load, I output, and also this is the voltage output. Okay, so transfer utilization factor is the one which is VSIS supply is in the denominator. So it's actually apparent power, output power over apparent power. And also we have power factor. That is here. This is the DC one. However, if you look at that one, this one is power factor. Power factor is the parameter important parameter as far as primary side of the system is concerned. Primary side. So you actually give active power, but some of the power is used for reactive components. So the apparent power is higher than active one, and it tells you how much ripple actually you have in your primary side as well. Crash factor is something different. I'm going to explain it. I'll do it right now. I'll do it right now. But please listen carefully. Assume that the crash factor, you have to understand the crash factor, since in most of the power electronic rectifiers, we use sinusoidal input power factor corrector. Sebebini söyleyeceğim şimdi. Dikkatli dinliyorsanız eğer, önce bir siyahla bir dalga şekli hazırlayayım. Ya da bir devre çizeyim önce ya. Devre. We have supply voltage. We have supply voltage. Başıma bela oluyor. Bir yazı çıkıyor. Siz görebiliyor musunuz o çıkan yazıyı? O yazı çıkınca ben yazamıyorum. Kalemin önünü kesiyor. Yazdığı zaman da saçma sapan bir şey çıkıyor. Şimdi şu rectifier olsun. Bir tane anahtar koyacağım çocuklar. Bir tane diyot koydum. Tamam mı? Yok, gerek yok. Bir tane diyot koymaya gerek yok. Devreyi çizmeyeceğim buraya. Sadece konsepti vereceğim. Şimdi burada bir rectifier var. Burada gerilimi düzeltsin diye bir kapasitör var. There is a capacitor connected. So that one is load. Since and this capacitor is charged, let's assume that. Since your waveform is something like this, but if you have the capacitor or a battery is fully charged like this, we see, then what's going to happen actually? The current is going to flow in this part. So that one this one is equal to Vm sine omega t, but that one is Vc, and Vc at this point, for example, at this point is higher than the actually instantaneous voltage, which is that instantaneous voltage is rising here. So only that part, only this part, rengini değiştirelim. Only this part and this part current is going to flow. So this moment and that moment is defined like this, and the current, I'm going to draw it in blue color. Current IS, şuraya da yazayım, IS, blue color. Current is something like this. Bu iki nokta arasında kalır current. If current becomes like that, şöyle, so current peak over current, since there are, so current waveform is something like this. Aşağıya çizeceğim çocuklar. Şu pi olsun. Şu da 2 pi olsun. Omega t. Veyahut da time scale'da burası 10 that one is 10 millisecond, that one is 20 millisecond. Current waveform becomes like this, depending upon the value of the capacitor connected. Current waveform is going to be something like this. If you draw it from supply, it's going to be, of course, in negative supply current, IS. So that means RMS value of this waveform is very low, but the peak value is high. This is the peak value. So the crest factor, this kind of waveform, we don't like it. We don't want to draw that kind of current from the system. We prefer a sinusoidal value. We prefer this one. We prefer to do that. So we add an electronic network somewhere here. It's called, we add an electronic network somewhere here, and it's called power factor corrector. Şuraya yazayım, power factor corrector. Sinusoidal input is required. Is required. Okay. Şimdi, so this is my just brief summary. Form factor, ripple factor, and also RMS value of the output current voltage, and DC average value. These are DC side. These are DC side. Tabii size göre galiba böyle göstermem lazım. These are DC side. However, for AC side, for input side, we have to look at the input current, we have to look at the power factor, of course, RMS value of the input current, RMS value of the input voltage. Input voltage is generally sinusoidal, and the apparent power inside the system. However, it's not equal to the active power you transfer to the load. I'm going to come back to that point. I know it is not very easy to understand right now. Just consider, I omit this one, we have already done it. Now, if you have a system like this, it's easy. The output, follow my cursor, current is going to flow through D1, resistance D2 for the first half. Then this is the transferred voltage to the load, and for the second half of the waveform, of the sinusoidal waveform, then the negative positioned diodes receives a positive anode cathode voltage, therefore they inherently conduct D3 and D4, conducting and transferring the inverse voltage. Inverse voltage means inverse of this one, and this is the output. That's the output for resistive load, by the way. There is no energy storing device in your secondary. However, if you look at of course, we can calculate that one. It's 2 over pi Vm. Bunu hiç sevmem ben. Şu sayılarla böyle yani Raşit niye sevdi bunu ben anlamıyorum. Yani doğrudan doğruya 2 over pi Vm. Bir kuralı var çünkü. Şimdi 3 faz yaptığımız zaman da göreceğiz. It's going to be 3 over pi olacak. 3 over pi. Yani pulse sayısı şeyi filan bunlar hep geçerli olacak. Evet. Devam edelim. Şimdi buraya geldik. Burada geçen hafta zannedersem şuradaydık. Değil mi? Çözdük mü denklemlerini? Ben tam çözdüğümüzü hatırlamıyorum. Buraya kadar geldik. Burada takıldık. Zaman bitti. Şimdi çocuklar ben bir şey fark ettim. Ders tahminimden yavaş ilerliyor. The course is progressing slower than what I was expecting. Of course, there is a reason behind this. Last week, the week before, I used to use camera, but now I'm deriving the equations. Although when I was using camera, I was writing the equations by hand. Writing the equations by hand with using pen and pencil is much faster than. Although I have a very good table here, pad here, so I can use this one, and it has a special let's say pen. However, there is a knob here, always problem. Anyway, when I write with this one, it's becoming slowly, but nevertheless I have to write those equations. So now, if I come back to camera, then what you are going to do, if I come back to camera, what you are going to do, you are going to take the picture of the, you see, system. I didn't know that last year or the year before, but you, the students, probably you told me that it's not storing the, when I show things in the camera, it's not stored in all-learn system. I don't know why, but that's their fault. Anyway, what's happening here? There are two cases. One of them is continuous current mode. The other one, discontinuous current mode. For starting with continuous current mode. Bu. Discontinuous current mode aşağıda. Bu. Biz continuous current mode'u bir yazalım bakalım. Şimdi yazıyorum diferansiyel denklemi. Benle beraber yazmaya çalışın. Önce şu şeyi bir yazalım. Buraya yazalım şeyi. VS VST, bu çok bold, fazla kaçtı. Düşürelim bunun şeyini birazcık. 2 punto mu? Bu 2 punto mu? Yok canım. Allah Allah. Olamaz ya. Evet tabii çok büyüttük ondan. Peki. Güzel, 2 punto dursun o zaman. VST is equal to VM sin omega t. Tamam. Şimdi however for continuous current mode, yanlış yazdım. Düzeltirim şimdi. Mode. Continuous current continuous current mode. Bir dakika ya. Ben niye continuous ya? Yani binlerce defa yazdığım şeyi yanlış yazdım ha. Tabii, tabii yanlış yazmışım. Google'dan kontrol ettim. Rezalet, rezalet, rezalet. Enteresan çocuklar ya. İnsan yani binlerce kez yazdığı şeyi nasıl yanlış yazar? Düzeltiyorum. I make the correction. Continuous. Evet. Şimdi yazıyorum denklemi artık. Buralara bir takım noktalar düşmüş. Artık onları da silmeyi vereyim. Tamam. Şimdi voltage, if you follow this line for Kirchhoff voltage line, you have to start voltage line. You have to start with minus VO. However, ben onu sol tarafa alıp hemen VST is equal to, there are two voltage drops of the diodes. I neglect those. Ri plus L di dt plus E. That is the differential equation. Solution nedir? Solution is something like this. I is equal VM, buraya sığmaz bu. Neyse bir sığdırmaya çalışacağım. VM over Z sin omega t minus pi. This is steady state solution. Minus E over R. This is also another steady state solution. Source. Plus T over tau. I always use tau But Mohammed Rashid in his book use, instead of tau, which is equal L over R, the time constant, he used, since L in denominator, you have L over R, he used R over L, put R in the upper part of the numerator part, R over L. I always use time constant, okay? So that is the solution. That is a general solution, but there's a constant here. This is transient. That one is transient solution. And that these two are steady state solutions. Now, in order to solve those, if it is a continuous current mode, so time equals 0, I'm going to put time equals 0 here for continuous current mode. Omega t is equal to 0, then current is equal IO. If I put IO here, I will obtain the current equation. For that one, if omega t is equal to 0, this one becomes minus. So I can calculate the K. K bakayım sığdırabilecek miyim buraya K'yi? Bu K'yi buraya sığdırsam çok iyi olacak. By the way, Z neye eşit? And phi neye eşit? Do you know those? That is the Z, amplitude of the resistance square plus omega L square. And phi here is arctangent omega L over R. So the constant here, K1 for initial value, K1 is equal to IO, initial current. That's the value here. You can see that. Follow my cursor, please. That is the initial current, IO. Plus E over R minus Vm over Z sine theta sine phi. Burada T over tau var. Bu da T yerine, if you put insert omega T here, so omega And if you divide it, so we are drawing k here, so this goes down to the bottom and then goes up with changing the sign, e to power omega t time omega t is equal bir dakika burada bir şey var. Burası 0 oluyor o zaman. Peki omega t equal i0 koyduk. If you put omega t equal pi, if you put omega t equal pi, what's the value here? Pi olduğu zaman burada gene IO. Tamam mı? Bakın bunlar pi olduğu zaman da IO. So eğer bunu kullanırsanız oku çekiyorum buraya. Değer e üzeri pi over omega tau çıkar. Omega t yerine t is equal pi over omega çıkar. Tamam mı? Şimdi constant'ı bulduk. Solution biliyoruz. Şimdi solution'u ben genel solution'u bir kırmızı içine alayım. Her taraf simsiyah oldu. This is general solution. That is general solution. And that one is K1. So if you put it there, you are going to obtain, you can see that IO has the solution of the form. This is a general. You can see that there is a constant here. You remember my equation. I use K. Biraz büyüteyim, görün. I use K here. So this is a constant. This is steady state solution because of the DC source. During face-to-face teaching, I used to ask a question to my students: why we did not divide Z instead of we divided by R for a DC source? For a DC source, there is no AC component. Therefore, only R is used. The answer is this. However, that one is steady state. This one is steady state solution, by the way. This one is also another steady state solution. Since we have two sources, don't forget that. This one is steady state, sinusoidal steady state solution, where teta'yı yazmamıştım. Burada yazmış olayım. Okurken, çalışırken yorulmayın. Gerçi bunları biliyorsunuz ama theta is equal arc tangent omega L over R. Time constant is equal L over R. Zeta R square plus omega L square. Of course, Z here is not a complex quantity, by the way. So this is the solution, exactly what I have already obtained. That one. And if you put that solution, then you are going to obtain this one. IO is equal to, this one is RMS value. That's why it's peak value. Here you can see that peak value is multiplied, sorry, peak value, instead of peak value, if you use RMS value, you have to multiply with square root 2. So RMS value is square root 2 times smaller than, for sinusoidal, by the way. Anyway, this is a steady state solution. This is transient solution, and that is also another steady state solution. So this is the final output. I derived that one. Okay, we haven't jumped the solution. Okay, so for continuous current mode, that kind of waveform we get. Artık şey yapıyorum bunu. Siliyorum. Çünkü dalga şekillerine bakacağız. Biraz da büyütüyorum. We have that kind of waveform. It's a continuous current mode. If inductance is higher, which inductance always tries to reduce the current variations, stores energy inside it, and if the value of E is not very big, I'm going to evaluate the conditions for this one. Then you have the continuous current mode. For this continuous current mode, however, what are you going to do? You are going to have a waveform like this. That waveform is not correct. I'm going to prove it to you. That waveform is not correct. This waveform is only valid, only correct if the load is, bunu ben yazdım buraya. If the load is a simple model of a battery, only R and E. Şimdi denklemi, çocuklar, bir şey opinion almak istiyorum sizden. Şimdi denklemi şey için çözüvereyim mi? Yani takip edebiliyor. If you follow me, I do not hesitate to spend more time. The more important thing is whether you understand the topic. Second, you are not involving, your brain is not involving a detail. So you should not forget, you should not miss, rather, you should not miss the overlook capability of the topic. Overlook capability. That's I'm I've been teaching more than 30 years. So that, of course, in distance teaching is a challenging. I can't see your eyes. That's the problem. I can't see your faces. I can't see your eyes. So that's why I have to ask you: shall I derive that equation here for this continuous current mode? Nobody's answering. Are you there? We have 24 students in our classroom. Evet, demek ki tam olarak şey yapmadınız. Şimdi o zaman ben bir boş sayfa açayım. Şu discontinuous'u bir tam anlatayım. I'm going to explain the discontinuous current mode. These are important circuit approaches. You have to understand, okay? Sorry about that. Just a moment. I'm not drawing the uh, bridge, single phase bridge rectifier circuit. I'm just going to write the equation and waveform. Now we have input, this is input voltage, Vs. So waveform is something like this. So waveform is something like this. It's omega t, that is pi, that is 2 pi. Okay? And the V S T is equal Vm sine omega t. All right. Now, assume that we have a voltage source here. Since it's a LRE network, we have this is E. Now I have a question. Is your diode connects at time equals 0 or not? Is your diode will start conducting at time equals 0? Çocuklar derste miyiz? Orada mısınız? Are you there? Nobody is answering my question. I'm asking the question. What's going to happen at this moment? Peki, o zaman iyice basitleştireceğim olayı. İyice basit. Bir şeyi anlamak, yes, tekrar edeceğim. Diyorum ki şu anda mesela kürsörün olduğu anda acaba akım geçer mi? If whether the current is going to flow or not. This one is current waveform, by the way. I haven't drawn yet. Yani ne bileyim 7 volt, 8 volt. Ne demek 0.7 volt? Kim yazdı? En azından bir cevap aldım ya. İsmail. Ne demek 0.7 volt? Yani threshold demek istiyorsun herhalde. Peki. Şimdi bakın devreyi değiştiriyorum. Devreyi değiştiriyorum. Devre bu. Yani iyice basit bir devre yapıyorum buraya. Artı eksi DC. Sonra R, L. Tamam mı? Bu da load. Burada da bir diode var. Bu da Vs. Şimdi soruyorum size. Bu R niye böyle görünmez oldu ya? Şimdi bazı insanlar vardır, şekilleri çok güzeldir. Bazı insanlar vardır, şekilleri berbattır. Ben şekilleri çok güzel olmasa da iyiler arasındaydım İTÜ'deyken. İyi şekiller çizerdim. Ama burada olay zorlaştı tabii. Yani bu kalemle pad üzerinde çizmek. Çünkü ben şu anda ekrana bakıyorum ama kalemi görmüyorum. Yani kalem sağ elim idare ediyor işte bir şekilde. Şunu arı buraya yazayım da. Evet. Şimdi current is going to flow through that network. Current'ımızın rengi de madem öyle mavi olsun. Blue is the color. Is current flow between zero and that point? This point I call it alpha. Between zero and alpha, what is the voltage between anode and cathode of the diode? Since E is higher than Vs, this one is Vs is higher than the Vs. Therefore, voltage between 0 omega t alpha E or Vs t is smaller than E. If Vst, this voltage, supply voltage, is smaller than this, so a diode is reverse biased. No current is going to flow. But at this point, current is going to rise, alpha. So current is going to start I don't know when it's happening. Şöyle şuralarda bir yerde de bitireyim. Şöyle şurada bitiyor olsun. Beta, alpha, beta. This is the current. Okay. Now, how could I find the current equation? Of course, first of all, I have to know that when the current starts at alpha, so if I write the equation here, Vm sine alpha is equal E sine alpha is equal E over F, E over V, E over Vm. So you can obtain alpha. So alpha is equal to sine minus 1 E over Vm. When omega t becomes alpha, since that function you look at the function top. Vm sine omega t is the sinusoidal input, therefore here. So between those, from this point to that point, actually your instantaneous value is lower than E. Therefore, diode is reverse biased, no current. But at alpha, current is going to start. So how could I find the current here? It's obvious. The current equation here is this. Siyah geçeyim, çok mavi şey yaptı. Açık kaçtı. Mavinin koyusu yok muydu ya? Bu işte demek ki. Evet. Neyse ince çünkü. İnce yazıyor. 3 punta yazıyorum. Current is equal to, siyah geçiyorum. Current is equal to I is equal to Vm sine omega t minus pi over z minus E over R plus K times T over tau. Of course, tau is L over R. We all know that. We all know that here. But here, initial condition is this. If omega t is equal alpha, omega t is equal to alpha, is equal alpha, omega t is equal to alpha, I is equal to what? Kim cevap verecek? I repeat. If omega t is equal to alpha, I is equal to what? Bir cevap yok mu ya? Omega t alpha iken, this one is omega t is alpha iken, current is equal to what? Yani bir göreyim ya. Thank you. Muiz Hişam. Hişam mısın, Hisam mısın? Hişam değil mi? Isn't it Hişam?
Hisham.
Hisham. In Turkish, we also use Hashim. Do you have Hashim in? Is it Hashim popular in Arabic?
Yeah, there's Hisham and Hashim.
Hashim, yeah, okay. But you are Hisham. Okay,
Yes.
good. How do you spell Muiz?
It's Mu'iz. We have this letter Ain in Arabic.
Is it Muiz?
Yes. Yes.
Muiz. Yeah, well, I used to have a professor at Istanbul Technical University. His name was Muiz Eskenazi. Those Eskenazis, there are two types of Jews in Turkey. One of the Jews coming from Spain. When the Christians invaded Spain, after Arabic state over there, when the Christians took over Spain, they also hated the Jews, and all the Jews are immigrated to Turkey, Ottoman Empire time. It was 1,500 something years. Probably Moise is also used in Jews as well. But you are Arab. You are Arab,
yes, I'm
Muslim.
Arabic. Yes,
okay.
I'm Muslim.
Okay, good. Now, I just wanted to take a break. That since you are losing your concentration, gentlemen and ladies. I don't know how many ladies do we have in this one. So I start from very. I'm going to complete this part, and then I'm going to take a break. So if you have a source like this, that E voltage source, you can see that. Follow my cursor. That source positive potential is in the upper part, so it's opposing the diode terminal, opposing Vs. So diode cannot let current flow through between 0 and alpha. When the instantaneous voltage grow and reach the equal E, then it becomes higher than this, and then at alpha current starts. So since the current equation is this, it has steady state value, sinusoidal, and transient value. Then if you put omega t alpha, current is equal to zero, current equal to zero, current equal to zero, then we obtain K is equal to, inşallah yanlış yapmam, minus, çocuklar bu buraya sığmayacak ya. Şunları sileyim. Bakın bu alfayı burada hesapladık ya, orayı sileyim de buraya doğru gideyim ben.
Hocam, you mean whenever Vs is bigger than E, the current will start to flow, right?
It is, yes, that's
Okay.
absolutely is the case.
Okay. Thank you.
If voltage, instantaneous voltage is lower than E, no current will flow. So I write to K, the constant here is minus Vm uzatmayayım da yer almasın fazla. Şurada bir küçük eskiz yapacağım. Omega t is equal alfa, t is equal alfa over omega. Tamam mı? Şimdi buraya onu yazacağım. Omega t yerine, so we put omega t is equal alpha is equal t over t is equal alpha over omega. So that's that. Follow my cursor, please. Can you see my cursor? So that term is equal minus alpha over omega tau, but it is minus, but since k is going to remain alone here, I put that one to the left hand side. I put this one to the left hand side. You can see that. Change the sign. And now this one is going to the denominator. So it can come to the up with positive sign. So I write that one. Bilmiyorum, tekrar edeyim, bir Türkçe söyleyeceğim. Sonra İngilizce, I'm going to repeat in English again. Şimdi çocuklar, şu ifade, bakın K'yı yalnız bıraktık burada. Bu ifadede T yerine alfa bölü omega koyarsan bu alfa bölü omega tau olur. Ama eksi işareti var üstünde. Şimdi K'yı burada yalnız bıraktığımıza göre bu sol tarafın, eşitliğin sol tarafının paydasına gider. Paydada olan bir eksponansiyel terim eksi paya artı olarak geçer. Tamam. Şimdi I repeat in English. If you keep that one k alone here, that term goes to the denominator of the left hand side of the equality, and if it has a negative sign in denominator, so goes up to the numerator with a plus sign. So I wrote e to power alpha over omega tau. This is k. Okay. So if you know the solution, so if you put k here, you obtain the current equation. So the blue current is obtained. But what are you going to do now? You are going to obtain beta. If you put omega t is equal beta, current is equal 0, then you obtain the beta point as well. Okay, so the current is not a sinusoidal one. This current is not sinusoidal. It has sinusoidal component, it has some kind of DC component, but it's decaying actually a constant value, and also decaying that constant value, if you put it, is exponentially decaying. So is reducing while time is running out. So you can obtain the beta. You cannot solve that equation by hand. Therefore, it is necessary to solve it by iterative methods. Okay. So that is half. Since for this half, it is no possibility that I made it simple and put it only a single directed diode. Buraya kadar tamam mı çocuklar? If you understand that one, I will come back to the original.
Yes. Because
Thank you.
it's always gonna be under the E. Less than E.
Okay. So I come back to original teaching stuff. Şuradan alayım. If the load is resistive, it's simple. If load is inductive resistive, you have already know how to do it. But if your network is something like this, you have two cases. One of them, something like this, means R, L, and E. And the plus point of E, although is not shown here, E is something like this. So the diode D1 and diode D2, for continuous case, always start conducting, and that is the waveform we get as output current waveform. But as far as the discontinuous current waveform and supply, by the way, supply current is positive for the positive half and negative is the negative half, and it's very bad. You can see that it's not sinusoidal, but it is alternating current. And for the continuous discontinuous current mode, you are going to current is going to start from alpha to beta. However, you remember my calculations, you can see that this is not sinusoidal like this. This is not symmetrical like that. I repeat, follow my cursor. The alpha and beta is symmetrical in this picture. Since the model is R and E only, the battery. If it is a battery, you obtain that symmetrical model. So alpha, for example, alpha mesela 30 derece ise, if alpha is 30 degree, then 180 minus 30, 150. Beta is 150 degree, symmetrical. If load is R and E only, the battery model. However, if it is L, R, C, sorry, L, R, L, and E type of, then that equation is valid. This one is continuous current mode. I derived those equations. And this one is, I also add that note, discontinuous current mode. Then you are going to see that this is K. Look, that is my K. Of course, you have to multiply with time, time exponentially reducing time function. And this is another steady state solution. This is sinusoidal steady state solution. This is DC steady state solution. And in make it simple, then they derive that equation. Don't try to solve it. You can't solve it. Only iterative methods required in order to obtain beta. Yeah, that's right. This ratio X, there's a table in order to make it simple for us. X here for X is equal E over Vm. Bakın burada da eksik, pardon, eksi koymuş. Görüyor musunuz X? Ama yazmamış. So X is equal. Niye önemli X burada? Alfayı oradan bulduk hatırlarsanız. VM hatırlayın. VM sin alpha was equal E sin alpha was equal E over VM. Bir de grafik var. Şimdi that is the boundary between beta'yı bulmak için ya bu tabloyu kullanacaksınız lazım olursa ya da iteratif olarak deney yanıl metoduyla try and error method. However, that is also the boundary between continuous and discontinuous current mode. Load voltage ratio X here, if E over, so this is a step, this is continuous part and that one is discontinuous part. Biraz büyüteceğim çocuklar. Göremedim. That is theta. Load impedance angle in radians. Onun ve şeyin fonksiyonu, x'in fonksiyonu. Tamam mı? So eğer if x is small, small means E is smaller than V, so it's is continuous, that part is continuous and this part is discontinuous. That part is continuous and this part is discontinuous. Bakayım bir şey daha vardı burada. Gerek yok. Bu bilgiye gerek yok. Artık o kadar yeter. Spice'la çözüyor şey. Biz Spice vermiyoruz. Evet. Input'a geldik. Burada duralım. Yorulduk. Şimdi kaçta buluşalım? Evet. 10 dakika etmez herhalde bize. 10.35'te buluşalım. Tamam mı? Bir dinlenelim. 10.35. Ben de biraz kalkayım, yürüyüş yapayım, bir şeyler yapayım. Hep oturuyorum. Okay? 10.35. So input power factor is equal to input active power over RMS voltage and current. In other words, apparent power. Okay, so that is the equation we have. So that is a kind of misleading figure, where that is, be careful. This is sinusoidal. Follow my cursor, please. This is sinusoidal supply, and that one is assumed to be flat DC current. Therefore, this is the reflection of the flat DC current from primary side, the transformer input, or to the rectifier. That is the example. That's right. That is the example I'm going to solve, and I'm going to concentrate on the power factor with this example. So this is a kind of inductance where the inductance is dominant. Inductance dominant means your output is flat. You can see that. This is what you should understand at the very beginning. If we all know that actually the output is going to be, çizeyim, output is going to be something like this. Nerede o? Bir kalem. Evet. Kırmızıyla çizeyim output'u. Output böyle bir dalga şekli. Bu V output. But we are not interested in output, since we are interested in input. And if that one is flat, the current of the input current is flat. That one is input current. Sorry. Input current. Şu, neyse yazdım nasıl olsa. That one is input current. Input current. That one, however, output current. So what's going on if the current, şimdi siliyorum bunları. If current is something like this, current is something like this, flat, so half of it is taken by half of it is taken by the positive part. This part is through this part. Then for the negative part, then we have on the blue ile göstereyim. We are going to draw blue current, again this direction. Current direction is not changing, but it's coming from bir dakika, bir yanlışlık yaptım çocuk. So current direction is not changing in the load, it's flat, this part, but so this is altogether a rectangular waveform. If you have an input current, something like this, if you have an input current like that, what are you going to do? This is your input current. IS. What are you going to do if you have an input current like this? How could you evaluate that current? I first emphasize the problem again. I'm not sure whether you are following me properly or not, but if you have a rectifier like this with the inductance is dominant, that means you are assuming a flat DC current output, DC current, flat DC current, then this part of it is supplied in the positive part from the red one. The red one current is in this direction, and the blue one is the blue part is in opposite direction, supplied from, so positive and negative DC current is supplied from this. I have one question now. What is the energy direction in this part and in that part. What is the energy direction? Hepsini sileyim, kafa karıştırmasın. Bu sorun baki kalsın. What is the energy direction between 0 and pi and 2 pi from supply? Okay, I'm going to make a quiz. Not quiz, I mean, I'm going to ask you a question. Can you see my questionnaire test?
Yes, Hujam, we can see it.
Right now?
Yeah, it's power direction from supply.
All right, can you express your opinion? If someone did it, then it means you can see it. All right. All right, go on.
Hujam, it's not the same.
Who is speaking? Mohammed?
Muhammad, yes.
Okay. I can't say, I cannot answer Okay. Still 18 students couldn't be able to answer. Come on, hurry up. Alperen, did you vote? Did you answer the test? I don't know what's happening between you. It's yes, yes has started initially, then no, all of a sudden become very popular. Lot of no's came, and then uh, we have some further yes. Still, 14 students couldn't be able to give any opinion, express their opinions. I told you, no matter whether you are right or no, I'm not going to take any note for this. Please do it. If you don't do it, I always consider that they are open the classroom, enter the classroom, and they left. They are not following my course. Those 12 people, I'm suspicious. Some of them probably couldn't connect. I don't know, but you, I always become suspicious. The one reason why I'm doing this is to understand whether you are inside the classroom or not. Now, 12 student is not inside the classroom. This is what my interpretation is all about. Seven students said yes. 13 students, now 14 students said no. Still 11 students is not in the classroom. I also have seen that, have understand that some students are connected by cell phone. Cell phone is too small for this business. Why don't you connect with your computers in order to follow the pictures? Adel Bayraktar, Batuhan Berat, Cemile Nur, Furkan Öğretici, Hamza Muhammed, Muhammed Necati, Muhammed Abdülvahit, Mustafa Karaman. Are you there? Are you inside the classroom or just entered the classroom and then left? Okay. All right. It's okay now. So 9 students, which I declare their names, couldn't be able to answer. Some of them probably are not inside the classroom. 10 student, yes, and 14 student, no. So the problem is this: power direction from supply to load is the same in the first half and the second half. Let's have a look. For the first half, current is something like this. Kırmızıydı galiba. Kırmızıyla çizmiştim. Current is something like this. So the voltage is positive. Voltage is positive. Current is that one. So it's actually energy direction is this. For the second half, voltage is negative. So voltage is, it was blue color. Voltage is negative. So the negative point has got a positive potential. And current is negative too. Current is negative too. Product is positive. So for this one, energy is in this direction. For that one, is energy is in this direction. That is why it's the energy is always from rectify the supply side to the load side. Burada da remember that there is always a positive voltage. Bakın, that one, current is positive and voltage is positive. Voltage waveform is something like this. Siyahla çizeyim de anlaşılsın. Hatta pembeyle çizmiştim. Onu düzelteyim. Hemen pembe yapayım. Pink. If you look at the load side, that is the output. I'm sorry. That is the output. All right. And this is the output. Okay. So average value of this one is positive. If you look at the load side, VDC, IDC, ikisi de positive, PDC is positive. So all the time energy is in this direction, from left side to the right side, input. There's no change. If voltage becomes reversed, current also reversed. Okay? So let's continue our course now. How could we understand the waveform, this current waveform, and how could we obtain the power factor? The simplest way for the power factor, I'm going to do it here. Power factor is equal to power S over apparent power. In other words, power S is approximately equal power DC. So IDC VDC. S, however, S is equal VS RMS times IS RMS is equal Vs RMS times Is RMS. So what's the RMS value of this current? What's the RMS value of this current? Is is equal to Ia square plus Ia square over 2 square root 2. Square of the function, get the average, and get the square root of it. So Is is equal to Ia. However, Vs is equal to the relation. What is VDC here, by the way? VDC şuraya sığdırabilirim gibi. VDC is equal 2 over pi Vmax. O da eşittir 2 over square root 2 times pi. Pardon, yanlış yazdım. Two over square root 2 times pi VDC. Buradan power faktörü başka bir kaleme geçeyim, karışmasın. Şimdi buradan devam ediyorum. Power faktör eşittir equal IDC IA. Tamam mı? IA is already known. IA. VDC 2 square root 2 times Vs bölü, burada bir pi vardı. O pi'yi aşağıya gönderdim. İnşallah yanlış yapmıyorum. Hiçbir yere bakmadan yapıyorum. Şimdi aşağıya gönderdim. Bunu yazdım değil mi? Bunu yazdım. Şimdi aşağıya IS yerine IA yazıyorum. IA. Ondan sonra VS yerine de VS yazıyorum. Bu VS zaten. Şimdi siyaha geçelim de kimler kimleri götürdü bir görelim. IA bir gitsin. IA'ler gitti. VS'ler de gitti. Ne kaldı geriye? Power faktör. Kırmızıyla devam ediyorum. I continue in red. What's power factor is equal to 2 karekök 2 bölü pi. Bir çarpın bakalım ne çıkıyor. Ben de şeyimi alayım. Hesap makinamı. Doğru mu yaptım, yanlış mı yaptım? Burada belli olacak. İki karekök 2 çarpı 2 eşittir. Bir dakika, yanlış yaptım. Karekökünü aldım. Tamam, 1,41 çarpı 2 eşittir. Tamam. 2,82 bölü 3,1416 eşittir. Evet, doğru yapmışım. 0,9. .9. Böyle bir diode rectifier'ın power faktörü 0,9'dır çocuklar. Nasıl yaptığımı anladınız değil mi? Yani şeyi neglect ederek output power'ı aşağı yukarı input power'a eşitledim. Ve oradan I used RMS value is equal square of the function's average value square root, which is equal itself. So I put those values in equation here and I obtained 0,9. I knew that the result. Şimdi başka bir yol daha var. O yolu now what we are doing actually, çocuklar bunlar önemli konseptler. Yani biraz zaman harcıyorum ama önemli konseptler. Çocuklar size radyo sesi falan geliyor mu? Televizyon radyo sesi benden.
Hayır hocam.
Gelmiyor değil mi? Tamam, çünkü bana kadar geliyor da aşağıdan ama yani size ulaşıyor mu? Yoksa yani çünkü kapıları falan kapatıyorum ediyorum bir şeyler. Şimdi gerek yok demek ki. Evet. Deprem konuşuluyor tabii. Feci yani. Evet. Şimdi çocuklar biz tabii konsantre olalım. Let's concentrate. So the case single phase, niye küçüldüm böyle ya? Single phase bridge rectifier flat load current case input current waveform and its harmonics. Topic is this. It's a single phase bridge rectifier. We all know that the current waveform is something like this. Ah, so this is the current omega t diyelim buna. That one is current waveform. So these are omega t's. Actually, this waveform has got components. One of them is a fundamental component. Fundamental. That one is the third harmonics. Third harmonics is the frequency. This is the frequency of this one for fundamental. F is equal F1, F1, which is equal 50 Hertz. For Turkey, it's 50 Hertz. However, for third harmonics, frequency F3 is equal 3 times F1. And for fifth harmonics, F5 is equal 5 times F1. And for seven harmonics, 7 times F1. So the frequency of third harmonics is something like this. Fifth harmonics, now consider that 5 times peak you are going to have. Hayda, şeyi shift etti ya. Maymuna çevirdi bizi ha. İstemiyorum oynamak. Allah Allah. So for the fifth harmonics, amplitude of the fifth harmonics is smaller, and however frequency 5 times higher. I draw the waveform. This is the frequency is 5 times higher than this. Okay. 7 harmonics, the amplitude is even smaller than this, but there are 7 peaks here. That one plus this one plus that one plus that one would yield this square waveform. Okay, so these are called, the analysis is called Fourier analysis. You know that one. So square wave, these are called Fourier components. How could we get the Fourier components? This is what I'm going to do now, right now. I'm going to be a bit fast. Evet, inşallah bir aksilik olmadan sığdırabiliriz bunu. Biraz yorulacağız. 2 punto. IST is equal to IDC plus N 1, 3, 5, infinite. in cosine in cosine n omega t plus Bn sine n omega t. You remember the Fourier analysis. IDC, since positive part and the negative part are equal, IDC is equal 1 over 2 pi integral from 0 to 2 pi IST d omega t, which is equal to 1 over 2 pi from 0 to pi IA times cosine n omega t d omega t eşittir 0. DC component is 0. However, IN is equal to 1 over pi from 0 to 2 pi integral IST times cosine n omega t d omega t, which is equal to 2 over pi from 0 to pi IA cosine n omega t d omega t, which is equal to 0. IN is 0. Bn is equal to 1 over pi integral from 0 to 2 pi. In that case, IST times sine n omega t d omega t, which is equal to 2 over pi from 0 to pi IA sine n omega t d omega t. Buradan Bn equal 4 times IA over n pi. So solution, renk değiştireyim biraz dikkatinizi çeksin. Solution is this. IT IST equal 4 IA over NP times sine omega t over 1 plus sine 3 omega t over 3 plus sine omega 5. Sorry. Gördünüz mü neler yaptı? Aynısını kopya etti. Demek ki bayağı bir kabiliyeti var. Ben o kabiliyetini bilmediğim için bundan cebelleştim. Siliyoruz tabii o kabiliyetini. Bize lazım değil. We don't need those. Evet, sığmıyor nasıl olsa. Bunun için daha fazla uzatmayacağım. Buradan IS1 IS IS1 the first component is equal to 4 times IA over NP, and N is 1, so pi tam eğer RMS ise bu IS max diyeyim buna. IX max is 4 times IA over pi. IS1 IS1 RMS is equal to, it's a sinusoidal function. We all know that for sinusoidal functions, RMS value is the relationship between peak and RMS is square root 2. Peak is square root 2 times higher than RMS. So RMS is smaller than peak 4 times IA over pi square root 2. Bu da 0.9 times IA. Bakayım yer var mı aşağıda? Evet, bayağı güzel yazmışım. Küçük küçük. Bayağı yer var hala aşağıda. Ama biraz şey yapmam lazım. Yine renk değiştirmem lazım. Çünkü hep aynı renk şey yapıyor. Yoruyor. IS-RMS is equal to 4 IA over pi square root 2 times 1'in karesi artı 1 bölü 3'ün karesi artı plus, I'm sorry for Turkish, 1 over 5'ın square root of 1 over 5 plus 1 over 7 square, so on. Bu 1 bölü 9'u da koyayım. So that is the RMS value of total value. So in order to find the total harmonic distortion, denklemleri gelecek biraz sonra. We are going to learn the equations when I come back to original. For this rectifier, so what we have done so far, I just repeat, we employed those square waves, the Fourier analysis, we for the input current, flat load case, current is constant. So DC current is obviously, there is no DC component in it. Buraya bir not düşeyim. Şimdi kafanız karışır sizin. Bir İngilizce, buraya bir kırmızıyla bir şey yazacağım. Component of supply current. Bu sığmayacak buraya. Burada yer çıktı. Okay. DC component of AC current of supply current is 0. Not the DC output. Şuraya da bir S koyalım ya. Supply'ın DC'si bu. Mavi renk. Geri dönüyorum. Is Fourier analysis is alright. So square wave is analyzed and obtained that it is actually combination of number of different frequency sinusoidal waveforms. The fundamental one has got the same frequency, but the third harmonics has 3 times higher frequency comparing with the fundamental. Fifth harmonic has fifth order of the frequency, seventh harmonic, and the amplitude is 1/5, 1/7, 1/8, sorry, 1/9, so reducing as well, but the frequencies are getting. If you combine those ACs, sinusoidal waveforms, you will end up with DC. This is what Fourier analysis is all about. Why we use the Fourier analysis here? I'm going to come. I dropped the line. Now I come back. Okay. Şimdi nereye gideceğiz? Geri dönüyoruz. We come back to our original course material. I'm going to make a start, fresh start now. Listen carefully. I'm going to be moving very fast. Output might be something like this. Not always a flat DC, all right? But it might have AC components in it. When you employ Fourier analysis to the output of this waveform, I might give you an home assignment for this. You can do that. You obtain the harmonics of the output as well. I solved the input harmonics, by the way. And we all know that quantity of the output is a DC voltage and current power, and also it has an AC, the RMS voltage and RMS current is higher than these pure DC values. It gives you the input power. An efficiency of the transformer or rectification is not transformer, rectification is a DC over AC component. AC means the RMS values of the current, and also we can see the ripples as well. The form factor and ripple factor is defined accordingly. The AC component of the DC is what we don't like. Therefore, we prefer our ripple factor should be 0, but it is not. And the relationship between ripple factor and form factor is this. Form factor is higher than 1, so we prefer, or form factor is 1. This is transformer utilization factor, the output power over input apparent power. And power factor is active power divided by VSIS, and crest factor is the peak value over input. These are input current quantities. We already have seen the average voltage of this rectifier. The diode rectifier is center tapped, but also each diode, if it is open, gets the 2 times of those voltages. Okay. We already calculated this 2 over pi Vm. The bridge also we calculated the average voltage, and also we have seen that the voltage of each diode when the diode was open is equal to the supply voltage peak value. But average value was 2 over pi Vm. 2 over pi Vm. Okay. And also we studied continuous current mode analysis of R, L, E types of work or loads. We analyzed that one. We also analyzed this case. It is, that one is discontinuous current mode, this case. But this simple example, since alpha and beta is symmetrical here, is not the one I sold you. It is R and E only type of load. So we have seen that load is actually changing the waveforms. We concentrated those equations. We have already derived those equations. And also we have seen continuous current mode, and the discontinuous current mode is also a function of E, the voltage, opposite voltage, and also the function of L over R. If L is higher than R, or E is lower value of E, it's a continuous current. And this is the boundary. That is the boundary. That's the boundary reflecting that. And that these are also saying that X, you know that X is equal E over V max square root 2 times Vx means that V max. Spice example is not you are responsible. That is input power, input side, input current, that one, this one. For the flat rod, I analyzed that waveform with Fourier analysis, and I shown that we have odd harmonics. In Turkish tek sayı harmonikler 1, 3, 5, 7, 9, 11, 13. So 1, 3, 5, 7, 9, ninth harmonics, 11th harmonics, 13th harmonics, and so on. Higher the harmonic order is the lower the value. We have shown that. Tamam. Kim girip çıktıysa fark etmez. Displacement factor for sinusoidal waveform is cosine phi. Harmonic factor is, gördünüz mü harmonic factor'ı? IS, which is, biraz büyüteyim. IS minus IS1, that means the rest of the harmonic factor actually is this. Tamam mı? Bu da IS1 square minus 1. N is a harmonic order. Çok az zamanım kaldı. Yürüyorum. Burayı hallettik. Power factor, eğer varsa bir fay, bu çocuklar, bu çok öğretici değil ha burası. Power factor aynı zamanda bu şeyi, phase shift'i de bu ancak, buraya ben bir not düşeyim, çalışırken belki faydası olur size. For fully controlled rectifier, there is alpha delay angle. Bu yani iş çıkarmaya başladı. Delay angle. Then power factor IS1 over IS. Of, niye böyle yapıyorsun ya? Gene bir işler çıkardı başıma. Dur bakalım. Bu kalem akıllı. Ama fazla akıl iyi olmuyor işte, gördüğünüz gibi. Yani fazla uyanık benim başıma bela oluyor. Kendi başına parmağım şeye değince batıma, hiç beğenmedim burayı. Baştan yazacağım. I'm going to write it again. Kosinüs pi falan değil. Doğrusu bu. Tamam mı? Evet, burayı basit Fourier analizi yapmadan, without a Fourier analysis you can solve it. But with Fourier analysis also we have seen that IS1 is equal 0.9. So 0.9 times IS. So it's 0.9 times cosine alpha. Alpha is 1 for diode. Cosine alpha is 1 for diode. So power factor is 0.9. But I also showed you, proved that this is the simplest method. In Turkish, karelerin ortalama değerinin karekökü. Square of the function, get the average, then square root of it. Okay. Root means square. En sondan başlayın. Square. Mean root. Okay. This is what we have done. I have already put that one to you. And also I have proved this one to you. Oh, that's right. But before than this, I'm not going to start multi-phase example. Before than this, next week, I'm going to complete controlled rectifiers as well. So I'm going to provide the delay angle. Okay. I was thinking I'm going to reach to the bridge, three-phase bridge rectifiers like this, like that one. But unfortunately, I couldn't be able to reach that one. Anyway, I'm going to take a attendance list. Moment. Kopyalamadı ya. Allah kahretsin ya. Bıktım vallahi. Niye hepsini kopyalamıyor ben anlamıyorum. Don't leave. Almıyor ya. Almıyor. Neyse not ettim. Muhammed don't leave. Muhammed Abdülvahit'ten sonra tekrar alacağım. Don't leave. The last person is Yusuf Selim. The first person is Abdul Bari. Okay. I've got it. Okay, thank you very much for attending the course. Follow, if I give you home assignment, follow the home assignment, okay? I might make a quiz, so study those material. I might make a quiz next week. I don't know. All the best. Bye-bye. Stop the recording.
Hocam, do you have a lab session today?
I'm sorry, I couldn't understand.